Okay. Again, this is Mr. Hayden. This is physics. I would really like for you guys to actually start coming in person if available, or if you're able to. I know none of you guys really have D's or F's, so you don't have to. But it'd be nice to get you guys in to be able to get this taken care of. I know we have some labs coming up that you'll probably be in for, but just be nice if you guys start showing up. This isn't just for you. It's for the other people that will be watching this recording as well. So let's go ahead and get going. Yeah. So the essential question that you're going to turn into the class is basically, what is the difference between an elastic and inelastic collision? So when two things hit each other, a couple things can occur. One is that it can either hit it and bounce off of it, but it still absorbs some energy, or it can bounce off perfectly. So that's a true elastic one. Now, an inelastic is when it hits it, it actually combines or becomes a part of it and moves with it, typically in the same vector direction. So those are some of the parts there. So we're going to learn about linear momentum in collisions. So you can obviously see here that there's a collision that took place from a car, and the collision. This is the collision on the car. And obviously going in this direction, and obviously things hitting in this direction, and it creates a vector in this direction. Those are just x, y movements of velocity, it looks like, and be able to use the Pythagorean theorem to figure out the direction, angle, as well as the velocity and the other angle. But the actual collision taking place here will be both an inelastic and elastic, depending on the situation. If they hit each other and they kind of combine together and they absorb together, that's going to be an inelastic one. Now, if they hit and they bounce off and there's no damage at all to the other car and all energy is perfect, which never happens, but in a pretty much a perfect situation, that's going to be the inelastic approach. So let's go ahead and look at a few of those. So we'll also be looking at not just linear momentum, we'll look at Newton's second law, look at impulse, conservation of linear momentum, inelastic and elastic collisions. So when we talk about momentum itself, okay, momentum basically is a mass with a velocity and actually in a certain vector or direction. So remember, it is a vector. You typically have to have a direction such as it's going north or west or east-west or whatever it is or whatever angle. So it's not just an acceleration and it's not just a movement. It's a movement with direction. So changes in momentum. So if we look at A, you see that there's a mass velocity, and it hits little guy right here. Basically hits the ground and just sits there. Okay, there's no bounce, there's nothing. It just sits there. But when you look at the ball next to it, when it hits, it not just hits, but it also rebounds or pushes off. This right here would be one type of collision, which is an elastic, and this right here would be an inelastic collision because the energy is being transferred in a different vector or usually a negative direction. So Newton's second law basically, you can see there, is valid for objects that have a constant mass, so a mass that has to stay there. So here is more of a general form, also useful mass changes. We're not going to really talk about mass changing so much. Now impulse is going to basically be the average force of something over time. So for example, if say something's getting pushed in a certain direction, it's going to want to change direction, what we'll do is we'll create an impulse or a velocity in a different direction, and that velocity is based on the amount of time. If it's timed to a certain point, it could be stronger or lower. So example, if you watch like Apollo 13 or whatever that movie is, and you're watching it, they'll actually start to use impulse rockets or little rockets to create impulses to change their momentum to be able to go in a certain direction or a certain vector. When you look at this, you can see here it's just basically is the change in momentum over a certain amount of time. You can also look at the inside the class to get some more figures with that. An impulse, the example here, is a baseball that has a certain momentum coming in, and the only way to change the momentum is if that bat actually hits the ball and creates a impulse in the opposite direction. It changes the momentum in the opposite direction, which an impulse had to occur to change that. The amount of time it takes at that point. Now, the more time typically it takes, the less force is because of the momentum. And when you start looking into K-12 and doing some of the math and stuff, it'll ask what is the time or whatever it is. One of the reasons why we have airbags or collisions, typically they'll try to let the front crumple of a car, or they'll have an airbag. So what they're doing is they're trying to create a lot of time between or an impulse in the opposite direction of where your head is going, where your body is going, and that time difference can save your life. All right, keep going. So example you have here, two different canoes, and this is a non-frictional situation. So force 1 and force 2, this guy is just pushing the boats in the opposite direction. Since they both have the exact same force newtons, when they push, whatever they exert on it, they'll actually push the exact same force in both the single direction and the opposite direction. And so they'll actually both have the same exact displacement because of that. If one of them, example, if say this right here had a newtons of 23 and this one of 46, it would be the distance traveled would be double than the distance traveled this way because of the doubling of basically the mass in the boat, or the least of mass in the boat. Inelastic collisions, when two objects strike each other, the time is typically very short, and other forces are ignored. Inelastic is momentum is conserved, but the kinetic energy is not. Complete inelastic is when they completely stick together. So when it hits, they actually become the exact same object, and then they continue on moving. So example of that would be a car or a train car slamming into another train car and actually becoming one train, and the forces continued in the direction or the vector that actually stakes. Okay, this is the same formula you have inside of your class. Definitely take a look at it. It looks at initial velocity and velocities of masses of two different objects coming together and be able to find exactly what it's looking for based on mathematics. Inelastic, again, is when it hits and absorbs into it. Absorbs into it. So again, this is an inelastic approach because they do actually not combine, but they become the exact same kind of locked-in car together because of that. They do not just bounce off each other in two different directions. They combine, and the force kind of manipulates into a single vector direction. Okay, so in an inelastic one is basically kind of like what happens with curling. Is you throw something over ice, it hits another object, based on where the mass of that is, it will change its velocity in a different vector. So if this bigger mass right here hits the smaller mass here, it will actually continue that velocity. Now this might actually still have a little bit more velocity left in it. It will definitely slow down, but it will transfer that velocity to the smaller one and push it on at a certain velocity. You can calculate that also by this formula here. The formula inside the K-12 class is a little easier to understand, so I'd actually go back there and use that one. But definitely write those down and be able to go into the problems and manipulate a field of problems to get the answers that you need. Okay, so here's the curling situation. Again, same thing as when you hit something on a certain line, it will create a perfect elastic situation, and they'll actually push in two different directions. They don't combine on the same vector. They're not inelastic. They actually did bounce off each other, which creates the elastic approach. So summary is just random, the stuff that we went over. Linear momentum is going to be mass times velocity. And then we'll look at the fact that impulse is the same type of momentum or impulse, but you calculate and put time in with it. Everything has a direction, or a momentum since it is a vector, everything has a direction. And momentum is conserved if the net external forces are zero, so energy has to be transferred, it just doesn't go away. All collisions assume external forces can be ignored. We do that just because everything's negligible, such as friction and such as air forces and things like that. Inelastic collision is kinetic energy is not conserved. They're basically combined into each other. Inelastic, this objects stick together and completely inelastic, and then move forward in the direction together. You can read the rest there. Elastic energy is completely conserved, and they bounce off each other in two different directions based on the angle that they approach each other. Okay, really that's it for this. That's the end of this slide or this session. It's a really quick one. Make sure you go in there and finish all the stuff you need for this week. Turn the essential question in the Dropbox to get the credit, and I'll try to publish on a YouTube channel for you guys to understand it completely.